coming to the other course, 102. And here we are coming to a very important question. Actually, I would dare to say a crucial question. So, how well behaved are sequences of functions or sum of functions if we know some properties of functions themselves, right? So, for example, so we have got something like a sum, infinite sum of functions, not necessarily power series, right? So I can have any functions, fn here. And there are many natural questions. So for example, if fn is continuous and the function sx exists point by point in an interval, so it converges on the interval. So if the functions are continuous, will the result be also continuous in some given point or in all points? Similarly, if the functions are differentiable at some point or everywhere, will the same property hold true for the sum or the limit of a sequence? So you see a sum of functions is the same of limit of sequence of the partial sums, so it's also a sum. And you see continuity of finite sum of functions is guaranteed if they are continuous, so that should work, right? So, but with the derivative it's even more interesting, because we are not interested only whether S is differentiable then, but we are interested whether we can differentiate the result so that we first differentiate and then sum. So we just come in. So that's something which we also already take as proven for the power series, right? But now in this presentation I will come with more general arguments which would just have all the properties of the power series as simple consequences. And the third question concerns the opposite to the inverse procedure to differentiation, the integration. So if I integrate the sum, can I do it by the terms and then have a sum of numbers instead? Right. Well, now maybe it will be a surprise, because the answer is that all three questions can be easily answered, and the answer is no. No way, you can't do that, you can't take this for granted. And so let's have examples, right? So it's always told in mathematics that like in gastronomy, so the real content is the real food, not only the impression how the restaurant looks, etc., right? Just what you get on your plate. Maybe there the look is also important, but the food itself is just why you go there. And here in mathematics is the examples of the usage, how useful the tools are, or if the answer is no, then understanding why. And here it's easy. So for example, take the function as here. So fn will be sine, and if you compute the limit, you see that it's like on the picture. So it's the power of, so n's power of sine is just the first thing, right? So, and that was for a series, for a sequence of functions. So from sequence of function in the example, you can easily make a sum of function just by doing the right things, right? So that's really simple, and the function sine to power k or n. So we go here for m equals n cubed, n goes from 1 to 10, and you see what's happening on the picture. And in particular, you see this. You see the point here, so this very value in the middle, in pi half, where the functions stay to be 1 all the time, independent of the power, but anywhere outside of that, they are at least slightly smaller than 1. And then with having the k big enough, they are as little as you wish. So the result, of course, the function which is the limit of this sequence will be simply looking like this. So it will be 0 everywhere except of one point where it's 1, right? So everywhere else it's 0, here it's 1. So it's not continuous. not continuous. Right, so that's the first example. Similarly, we can get the second one. The second one is just along a similar line. You see, so I have chosen the functions fn. So it's again a sequence of function. And for values n equals m squared, I get such a picture. And you see that whatever n I take, so along 0, so around this point, the first term, so this x, will dominate. Because all the rest will be in some higher powers, and so it will be more and more negligible the bigger the n is. But outside of that, this second half of the expression makes this bumpy behavior. And so you see it's always just going through the origin as the function x, but then it bumps back. And so essentially, if you look at the limit, it will be similar as before. So it will be just identical 0. I mean the derivative, right? So it's the derivative at 0 will be 1, right? So that will be the f dash. It will be 1. But for all the rest, you see the functions, if the n is big enough, you will be already in this very flat part. So the derivatives will go to 0. So everywhere else it will be just 0. Only in the beginning it will be 1. So again, the derivative is not the limit of the derivatives, right? So therefore, the property in the theorem doesn't work. The third example is just again along the similar line and working out the same thing with the integral, right? So we want to integrate, and what we do is we slightly improve the previous bumpy behavior. That was only the x times 1 minus x squared to n, was this special thing. And that's because if I integrate the things I had before, I get smaller and smaller values. So I multiply it with the constants so that the integrals would be always constant. Right? So, and I'm not talking not about sums but sequences. So all the integrals will be 1, but as you see, the resulting function is simply 0 everywhere, only here they will be approaching infinity. Right? So there will be, so the limit in 0 of the function will not exist, but who cares? And so, well, actually it will be over 0 again, but the bump will be higher and higher, so that will be even not continuous at that point on the boundary, right? So the limit function. Well, no, I'm wrong. So simply the bump goes through, it's higher and higher and higher, but in the limit, at every point here in the limit, it will be everywhere 0, right? So everywhere we come sooner or later to these very, very, very tiny values, and so the limit will be 0. So the integral is not the 0 which would come from the limit. So you see, in all three cases we saw that the answer is no. So why does this happen? So what was wrong on our examples? The wrong thing on our examples in all three cases was that essentially, I hate this. In all three cases, in all three cases, the speed of the convergence of the sequence of functions is simply different at each point, right? At this point, later and later jumps up to the 1 and then comes back. So convergence to the zero will be much slower than, say, here. And the same here, right? So the convergence simply is not behaving uniformly along the line, and even more visibly, it's the same here, right? The bump here will be growing, and it's very far from being uniform in speed, how quickly it converges to this constant zero. So we are at the concept of the uniform convergence. And it's something like, if you remember, we talked about uniform continuity, and it was one of the dramatical observations we did, and which simplified our life with the Riemann integration and many other cases, that if something is continuous on a compact, on a closed bounded interval, for example, then it must be uniformly continuous. So the control over how wiggly the function is, how quickly the values change when we change the arguments, are under uniform control. And here we want the same, so there will be a uniform control for the convergence independent of the point x, right? So we request that whenever we tell how much the functions differ from their limit, either in the sum or for the functions themselves, then there must be already an neighborhood of infinity, so some big capital N, so that for all bigger small n's, the elements in our sequence are already closer than by epsilon. Right, so this is, so the series of function converges uniformly on an interval if the sequence of partial sums does. Right, so that's the same for sequences as for sums. Right, and now this theorem simply says that, unlike our counterexamples, which work in general and say that in general the answer was no to all three questions, here the answer is yes. So if I have a sequence of functions which are continuous and converge uniformly on this interval, then the result is again continuous. If I have a sequence of Riemann integrable functions which converge uniformly, then the result is again integrable, and I know that the limit processes can be swapped, right? So I can either integrate the limit, which is just this, or I can throw the limit before the integral sign and first integrate all the particular members in my sequence and then make the limit, right? And it's the same result. And if it's differentiable, and assume that the functions, so now the third one is a little bit more complicated in formulation because it's actually using the antiderivative approach to the interval, and is a consequence of the second one. So we assume that at some point the original sequence of function was converging. We assume that they are differentiable, and we assume that all the derivatives are continuous and converge uniformly. And then we can say that there is the limit of the original sequence, which is computed by integration, and the functions converge to the f, and the derivatives coincide, right, as we would expect. So it computes the derivative. So in other words, we can find the function f, which is the limit of the original sequence. So remember, we assume that the original sequence converges only in one point. Now we know that there will be the limit of them, and we know that the derivative of the limit of the functions, which is the fx, is the same as the limit of the derivatives. So that's the nice theorem, and of course the same thing can be then reinterpreted for the series, and it says the same, right? So for the series we get the same thing, and again we just reformulate what we had there. So I will not read through in so line by line, doesn't make much sense. Right, so this is perhaps enough for the first bit for this week, and I will add another one in a second.